algorithm for F divergence minimization. Okay. This is what we are going to do now. So please recall that in the setup of generative modeling, the setup that we have is the following: that we are given a data set, okay, a data set denoted by D that has samples x1, x2 up to xn. So we have n data points that are all sampled IID from an unknown distribution Px, okay, unknown distribution Px. Okay. Now we have this particular setup where we wish to build a generative model. So goal is to learn to sample from Px, sample from Px, learn to sample from the distribution. And how do we do that? So recall the general recipe that we had. So we have a function represented using a neural network, a deep neural network. We call that g theta of z, where z is coming from any arbitrary distribution which we know how to sample from, and the output of this neural network will give you samples denoted by x cap, and we told that this we assume is coming from a distribution which we denoted as p theta of x cap. Okay. Now the goal is to, this will serve as a sampler for Px or a generative modeler for Px given p theta of x cap is same as that of Px, right. So how do we ensure that the above setup becomes a sampler for p theta, becomes a sampler for p theta, sorry, sampler for Px if my p theta is same as that of Px, right. So that is the idea. And how do we do that? We do that by solving this particular optimization problem where we fix the parameters of the neural network such that it minimizes the F divergence or any distributional divergence metric between Px and p theta. So we will choose F divergence here to do this. Now note that the algorithm that we are going to look at now is independent of the choice of f function that we make. So this algorithm works for any choice of f function that we make. So this algorithm is general in that sense. Okay. Now the objective is to come up with an algorithm to minimize the f divergence, okay, between Px and p theta, okay, Px and p theta. Okay. Now the other constraint that we have is, okay, without knowing both, right. So please note that this is the most important challenge that comes up while building generative models. This is a common problem that comes up in any machine learning paradigm, that you need to minimize, or rather you need to optimize over functions involving distributions and density functions, okay, but one would not have access to the actual density functions or distribution functions. So that is the key problem. No, but what do we have? We have, without knowing both of them, but having samples from them, right? So now we have samples that are drawn, okay, from both the distributions, because how we have samples from px because that's our data. We have samples from p theta because given any theta, we could sample as many points that we need from z and pass it to the g network and get samples from p theta. So maybe I'll just write that. So now samples from okay, yeah, samples from px is nothing but the data set d. Okay, so samples from p theta, what are those? They are the outputs of the g function of G neural network, in this case g theta of z, with or rather for different z's, for different z's. Okay, that's all. So we have samples from both the distributions, but we do not have the underlying distributions, right? Now note that the definition of f divergence involves computing an integral, okay, over the space of data, and the integral has both p theta and px in it. Okay. Now the challenge is that we neither know px nor we know p theta, and computing this integral is also intractable because the integral that we are computing, I mean, even though I've written that as a single integral, this is an integral over a d-dimensional real space, right? You have to integrate over each of the dimensions separately, and a multi-dimensional integral, that too with very high dimensions, is practically impossible to compute, right? So now the question is, without having access to p theta and px, and the fact that we are dealing with very high dimensional data, how do we solve this optimization problem involving divergence method? Okay, that is the question that we will be asking, right? Okay. Now the key idea is the following. See, this is a recurrent idea that comes up with all the generative models that we are going to look at in this course. Okay, I mean, this idea is actually a very old statistical idea that comes up recurrently with all machine learning algorithms. Is that um, integrals involving density functions in integral involving density functions can be approximated using samples. These can be approximated using samples drawn from the distribution, right? Samples drawn from the distribution. Okay, you all know this. The idea is the following, right? Suppose we want to compute the following integral. Okay, compute the following integral. Okay, so what integral do we need to compute? Let's say that we are interested in computing integral hx px dx, hx px dx over x. Okay, so now this is the integral that we are interested in computing, where h is any arbitrary function. Okay, h is a function or any function. H is a function on the random variable, and px is as usual the density function. Okay, right? Suppose we need to compute this integral. Let us call that integral some I. Okay, this is what we need to compute. Okay, what do we have is that we have samples drawn from px, samples drawn IID from Px. Okay, we have IID samples that we have drawn from Px. Okay, let us call them as x1, x2 up to xn, and these samples are drawn IID from Px. Suppose we have only this and we do not know what Px is. Can we compute that integral is the question. Turns out we can, because the integral is nothing but the expectation of the function h of x with respect to distribution Px, right? I hope that all of you know this definition, right? So if you want to integrate a particular function h of x with multiplied by a density function, okay, over the space of the random variable, then that particular integral is defined as the expectation of that particular function with respect to the underlying distribution Px. Now this is called the law of the unconscious statistician, abbreviated as LOTUS. Okay, right. So now what we need to actually compute is the expectation of a particular function with respect to a distribution, right? Now we also have this powerful result from statistics called the law of large numbers, weak law of large numbers. That would say that now if you have x1, x2, xn drawn IID from a distribution Px, then the expectation of, or rather the sample mean okay, all of these xi's are actually coming IID from I'll write in a different line. So now all of these xi's are being drawn IID from this the distribution with respect to which we need to compute the integral. Then if you have enough number of samples at the limit as n tends to infinity, this particular sample mean converges, or rather is equal to, approximately equal to the, okay, under the expectation this can become an equality, but if n is small, then I mean n is not sufficiently larger, then this becomes an approximation that this is equal to the expectation of this particular function h of x, right? So this is one powerful result that is used often in machine learning, right? The true expectation, okay, of a function of a random variable with respect to an underlying distribution can be approximated using the sample averages, okay, where the samples are actually coming from Px. So note that if these xi's are not coming from Px, this is not true. This is true only if the samples upon which we are computing the average are actually coming from the distribution with respect to which we need to compute the expectations, right? So that's the idea. So now if we use the law of large numbers, then the integrals that involve expectations of functions with respect to distributions can be approximated using sample averages, right? So now why is this relevant to the discussion that we are doing? So all we are saying is, if the f divergence or any divergence metric can be expressed in terms of expectations of functions with respect to Px and P theta, then one can compute and optimize them, right? So this is the idea. Okay, now let's recall. So our f divergence involved integrals. Yeah, see, the definition of f divergence involved integrals with p theta and px. Okay, Now, this cannot be computed because, as I said, we neither know px nor we know p theta, and these are integrals over the space of random variables, which are very high dimensional. But we also have this idea in statistics that would say that integrals involving density functions can be expressed in terms of expectations, and expectations can be approximated using sample averages, right? So, we only need samples from the distribution, but do not need the distribution to compute expectations. Now, putting all the pieces together, all we need to do is somehow represent the F divergence in terms of expectations involving p theta and px. If we can express the F divergence with using expectations with respect to p theta and px, then perhaps we can use the samples from p theta and px, which we already have access to, and compute the F divergence and optimize F divergence. So, that is the goal. It turns out that one can actually represent the F divergence in terms of the expectations over p theta and px. So, that is what we are going to see right now. Okay, so, now expressing the F divergence in terms of expectations over px and p theta. See, this is what we need to do right now. Okay, we'll see how to do that. Okay. Now, let us start from the definition of F divergence. So, this is going to be a little pedantic, so please bear with me. So, df, the definition of F divergence is as follows: integral over the space of random variable, we have p theta of x times f of px evaluated at from x divided by p theta evaluated at the same point times dx. This is the definition of F divergence. Okay. Now, I give you a rough overview of how this math is going to be. Now, please observe that we have p theta of x, which is a density function, right? And we have some function. Okay. So, please, if you compare this with let us say the integral that I had written before, which is x some density function times some function of the random variable x. So, this the definition of F divergence does not look similar to this. Why? Because while there is a function f which is similar to this some random function, some arbitrary function x, h. Now, the arguments for that function here was the random variable, or rather samples drawn from random variable. But here the arguments for the f function is the ratio of the density functions themselves. Okay. So, now it's you cannot write this, okay, as an expectation over p theta straight away, because this is not in this particular form. Okay. So, to do that, what is to be done is, so we have to somehow decouple this f function, right, from this px and p theta. So, somehow have to remove this px and p theta outside of this f function, so that we can get this F divergence in this particular form, which can be expressed as expectations. Okay. So, that is the whole idea of the algebra that we are going to walk through right now. Okay. So, now how do we do that? To do that, we need to first define what is called as a conjugate or a complex conjugate function, a conjugate function for any convex function, conjugate function for a convex function. So, any convex function, okay, would have a conjugate corresponding to that particular convex function. How do we define this? If f of u is a convex function, please note that u is a dummy variable here. F of u is a convex function. Then there always exists. There exists a conjugate function denoted by f star of t. So please note that t is also a dummy variable here, f star of t, defined as follows. Okay. Now f star of t has a pointwise definition. F star of t is equal to the supremum or the maximum over the domain of f. Supremum is of this particular function, which is ut minus f of u. Okay, so this is the definition of what is called as a complex a conjugate function of a convex function. So let me explain what this is doing. Now this is a pointwise definition in the sense that to get every point of the conjugate, one needs to solve an optimization problem involving the original convex function, right? I mean, this is what is known as a pointwise definition, where so you don't get f star of t just as some deterministic function of f of u, but to get every point of this conjugate f star, you need to solve this optimization problem over this particular function. Okay, that is the idea. Now, what is this? Roughly what happens is, suppose you have a function f of u, which is a convex function here. Let's say that f of u is a convex function. What we are actually doing is constructing multiple lower bounds, okay, for this function f of u at every point, and the value for f star of t would be that particular lower bound, okay, which is the tightest. Okay, supremum corresponds to, I mean, you can look into that as the maximum operation if the value is attained. Okay, now just for the understanding sake, I can actually write this as max over the domain of f. So what is u here? I mean, u is actually the optimization is over the domain of f. Okay, now as I said, u is a dummy variable here, which is signifying the domain of the original convex function. So what one is doing is, we'll write inside the parenthesis, what one is doing is constructing what is called as a conjugate function for a given convex function, okay, in a pointwise manner. So how do you do that? At every point, okay, one constructs multiple lower bounds on that particular u and chooses the tightest of all those lower bounds as the value of the conjugate at that particular point. Okay, so that is the definition of what a convex conjugate is. So now every function, every convex function would have a corresponding conjugate. Okay, now so there are a few properties that we need to look at of f star. So properties of f star, properties of the conjugate, properties of the conjugate. By the way, I did not define what a convex function is, assuming that people are aware of it. So maybe just for the sake of completeness, let me define what a convex function is here. Let me just write it here. A function f is convex. A function f of u is convex. So if and only if for all u1, u2 belonging to the domain and some constant alpha 1, alpha 2, which are real numbers. Okay, alpha 1 times f of u1 plus alpha 2 times f of u2 give me a second, is always greater than or equal to f of alpha 1 u1 plus alpha 2 u2. Okay, this is the definition of what a convex function is. Maybe I can make it to be convex combination. So what I wrote was a linear combination. Let us make it a convex combination. So any convex combination, for any convex combination, both the alpha 1 and alpha 2 have to lie between 0 and 1. So you take any number between 0 and 1, okay, and this is u2. Then for any points u1 and u2 that are in the domain of the functions, alpha times f of u1 plus alpha 1 times f of u1 plus alpha 2 times f of u2 should always be greater than or equal to f of alpha 1 u1 plus alpha 2 u2. So this is the definition of what convex function is. Okay, so let's get back to what we were looking at. So now every convex function will have what is called as a conjugate corresponding to it. So coming back to the properties of the conjugate f star of t. So the properties are that f star, which is the conjugate, is also convex. So one can verify these properties. The other thing is the conjugate of the conjugate. Because the conjugate is also convex, one can take a conjugate of the conjugate itself, will give back the original function. So these are the two properties that we'll be using. So this implies that f of u, what is f of u now? It is the conjugate of the conjugate. Now can be represented in terms of a supremum over the domain of f star, which is the conjugate of f, minus f star of t. Okay, please note that writing this tu or ut does not have any preferential ordering. So they are both dummy variables. All we are saying is that given a convex function, there exists a conjugate defined by this, and given the conjugate, which is also convex, one can take the conjugate of the conjugate, which will get back the original function, which means that original function now will become the conjugate of the conjugate, which is defined this way, right? So you can define the conjugate for any convex function this way. Now f star is the conjugate, and we are defining the conjugate of the conjugate, which means that my original function now can be represented in terms of the conjugate of itself. Okay, so now what is the relevance of this is this to what we are doing. So let us come back to the definition of the F divergence. The definition of the F divergence was as follows. We have integral p theta f of px by p theta dx. Now this is okay. This we will take this as the scalar u. Okay. So now this can be written as integral. Okay, this is over x. Maybe I'll skip this every time. So p theta of x times f of u dx, right, where u is the ratio of these densities. The ratio of these densities. Now we know that f of u, which is a convex function, can be represented in terms of the supremum or the maximum over T, which is the domain of f star, and the supremum that we take is of this particular function, right? This is something that we just saw, which means that I can write my f divergence. I will not write the arguments every time, in terms of integral p theta x times. There is a max, oh sorry, there is a supremum. Okay. I may actually write that as max, but yeah, there is a supremum over T, which is the domain of f star, and you have T times u minus f star of T. So please remember that u here is the density ratio dx. Okay, right. Now we'll unroll it. So this is integral over x, p theta of x times supremum over T, and what we have is T, which is a scalar, times you have px of x divided by p theta of x minus f star of T dx. Okay, right. So now remember what was our objective. Our objective was to represent the f divergence in terms of expectations. Now if we were to do that, then we need to have the form where there is a density and some function, and we still don't have it. We have a supremum here, right? So now to represent this integral in terms of expectation, we somehow want the supremum outside the integral, right? So that's what we will do. However, you look at this, we can't just put the supremum outside the integral. Why is that? Now note that this optimization problem, okay, is over T. However, the function that we are optimizing over has x in it, okay, and the integral is with respect to x. So which means that I just cannot bring out the supremum outside the integral, because the supremum that I am computing involves x, right? Now think about it. If you solve this optimization problem, okay, for a particular x, you get some t, which means that the solution for this inner optimization problem is a function of t. Therefore, if I bring the supremum outside the integral, okay, now the supremum is not with respect to t, but with respect to a function of x. So why is this a function of x? This is a function of x because the solution for this optimization problem that I am having will be a function of x, because this has x as its argument. So let me write that down. This will be some function t of x, px p theta of x minus f star of some function t of x. This is because the inner optimization problem involves x, and the solution for it is dependent, or rather a function of x, right? I'll reiterate what we just did. So this t was a scalar that we were optimizing over. Now suppose you solve this inner optimization problem with respect to t, you will get some solution for it. Now that solution is a function of x. So why is it a function of x? Because the objective function for this inner optimization problem involves x, right? Now if we push the supremum outside the integral, then for every x, right, the supremum has to evaluate in such a way that if you plug in that particular x, it will give you a t that is solution for this optimization problem, right. Because of the dependence of this inner optimization problem, the objective of the inner optimization problem on x, if I push the supremum outside, then the optimal or the search is not over a scalar t, but over a set of functions t of x, such that if you plug in a value for that function t, it has to give the solution for this optimization problem. Okay. Okay. So now this search is over a space of all functions script t. So what is script t? So script t is a space of all functions. So this should be from x to domain of s star, because the t, I mean small t, was a variable that we were using to represent domain of s star, right. What is this? These are a space of functions containing, or rather space of space containing solutions for the inner optimization problem. Okay, there's a space of function containing solutions for inner optimization problem. T of x is one member of this whole family of functions. So note that our optimization problem now is not over a scalar p, but over a space of functions. So what does that mean? It actually means that we are searching for a particular function from a space of functions. Think of this script t as a bag of multiple functions. Okay, and from all possible functions from x to domain of s star, we are searching for that one particular function that would give me the solution for this optimization problem at all x. That's all this supremum, I mean that is all the supremum over t of x signify. Okay, but there's a problem. So the issue is that while this is true, this may not be a strict equality. Okay, this will become an inequality. So remember that our RHS was the divergence measure, F divergence. Now this will become an inequality. So why does that become an inequality? Now the space of functions t, okay, that we are optimizing over may not contain the optimal t star of x that is the solution for all x. The solution for the optimization problem, right? That is the solution for the inner optimization problem. Right? What we are saying is that why we are searching over a space of functions from all functions from x to domain of s star, there is no guarantee that this space that we are searching over will actually contain that particular t star, okay, which would solve this optimization problem for all x, which means that this integral that is there, or rather the solution for this optimization problem that you calculate, may not be exactly equal to the F divergence. Okay, it can at best equal to the F divergence, or it will be more than that, because we are solving a supremum problem here or a maximization problem, right? So that's the idea. The idea is that this using the convex conjugate. Okay, so let me just copy this. Now, what did we show so far is that we created a bound on the F divergence. Okay, so let me just complete this. So this will be a supremum over T of x. Okay, and what is the integral here? If you just do the algebra, this would be integral p theta x times tx dx minus integral, sorry, this would be px, right? P theta would cancel away. So px dx and integral p theta of x times f star of tx dx, right? So now if you can appreciate, so what do we have inside the square bracket are nothing but expectations. So we have expectation of this function t of x with respect to px minus the expectation of this function f star of t of x with respect to p theta of x. Now this is what we have. So which means that we have achieved our goal, that we have expressed the f divergence in terms of expectations over px and p theta. This is exactly what we started with. No, let's look at our goal. Our goal was to express the f divergence in terms of expectations over px and p theta. We accomplished that by constructing a lower bound on the f divergence. Okay, so now this is the objective that we wanted to achieve in this particular lecture. So now we have expressed the f divergence in terms of the expectations over px and p theta. Now in the next module we will see how to use this formulation, okay, that we have come up with in building the generative model that we are interested in. Okay, so this brings us to the end of this particular module. Thank you all.